So to find that perfect ratio, we actually need a chart that shows what's called the zone of stability. Now you don't need to write this down. If I haven't already, I'll give you a paper copy that you can have. And what this shows is the number of neutrons versus the number of protons. And right here, this band shows the zone of stability. So any element that falls within this zone is by nature stable. So if we look at something like zirconium 9040 would fall right there in the zone of stability. That means it has 40 protons and it has about 50 neutrons, and so it's stable. Let's say that there was an atom zirconium, though, that had 60 neutrons instead. So if it had 60 neutrons, well, with zirconium, it would still have the same number of protons, but it would fall out there, outside of the zone of stability. So that means there's too many neutrons inside of that zirconium, and so it's going to undergo decay. It's going to find a way to lose neutrons, and so that it can get into the zone of stability. If an element has too many protons or too few neutrons, it would be down in this area, and so it would do something to get up into the zone of stability. And what you can see is right here, if you look at the beginning of the periodic table, the first 18 elements or so have a 1-to-1 ratio of protons and neutrons. But then at about that point, you start needing more neutrons in order to become stable, and then even more. So the ratio for zirconium is about 1.25 neutrons for every proton. But once we get up to something bigger like bismuth, you need 1.5 neutrons roughly for every 1 proton. And you'll notice that the band of stability ends right here. Okay, that point right there marks where elements just get too big. They become radioactive by nature. So too much stuff inside of the nucleus, they're going to decay in order to get down. This point right here is actually lead-206. So lead-206 is what all of the heavier elements, these guys out here, decay in order to achieve. All elements on the periodic table past lead-206 are by default radioactive. In fact, there's even forms of lead that's radioactive. Lead-208 would have too many neutrons, and so it would want to decay to get to lead-206.